In lecture 1, we will talk about four things: basic electrical quantities, active and passive elements, Ohm's law, and voltage and current divisions. We start with the basic electrical quantities. We have three basic electrical quantities: current, voltage, and power. We will define each of them. The current is the amount of charge that passes through the wire per unit time, or we can also define it as the movement of electrons or the flow of electrons. Electrons have negative charge. The formula for the current is dq over dt, where q is the charge and t is the time. The units for charge is coulombs, for time is seconds. So dq over dt, coulombs over seconds, gives us the unit of the current. It's amps, or we call it amp or amps. So 1 amp is equal to 1 coulomb a second. In circuit, how we see the current? We cannot see the current, but usually how we draw the current in an electrical circuit. As you see, this is the source. This is an element that we call it resistor. And the current, if the current is not given to you, you can draw it as an arrow that flows from this positive part of the source and continues in the circuit. As you see it, this arrow continues in this circuit and again returns back to the source. This is how we denote the current. There are two types of currents: direct current, DC, and alternating current, AC. Voltage. We can define the voltage as the energy absorbed as a unit charge moves from one point to the other. The formula of voltage is dW over dQ, where W is the energy and Q is the charge. The units used for energy, the unit of energy is joules. We measure it in joules, the charge in coulombs. dQ over dQ, dW over dQ, joules over coulombs. This gives us the unit of voltage. How we measure the voltage? In volts. In circuit, if we have an element inside the circuit, imagine this element is this resistor in a circuit, and there is a current passes through this element. When this current passes through this element, it leaves positive behind it. It means high voltage, and the other side of the element is low voltage. We will have low voltage. So when this current passes through the element, it leaves positive here, high potential, and negative is the low potential. This is the voltage. So see it in this circuit, and this is the current that passes through I. This is the current that passes through the element, resistor in this example. It leaves positive in the first part before it passes through the element, because still at high potential here, and here minus negative after passing it because it loses part of its potential. This is why we call it potential difference or voltage. The power is the time rate of expanding or absorbing energy. The formula of power is dW over dt. dW is the energy, dt is the time. This energy at this time. And we can write it as follows. What we do, we will multiply the numerator by dq and divided by dq. Why we did that? To extract the two quantities from the power. You see, dW dq, this is the voltage. dq over dt is the current. So the power equals V multiplied by I times voltage. This is the power. So to find the power, simply you need to have voltage and current. Circuit elements that absorb power have a positive value of P, but circuit elements that produce power have a negative value of P. We measure the current, as we said, in amperes, and the symbol for this, the unit of the current, the measure of the current is A, amps. We measure the voltage in volts, V, and the power, we measure it in watts, W. Elements in electrical circuits, we have in general two elements in any electric circuit: active elements and passive elements. Active elements can generate energy or power, such as voltage sources. The schematic symbol of the voltage sources is like this. This vertical bar denotes the positive polarity of the source, and the small bar denotes the negative voltage, Vs voltage source. Or we have another schematic symbol. We can also draw this schematic symbol as a circle, inside it plus and minus. So you can use this symbol or this one. The schematic symbol of current source is this circle, inside it is an arrow, IS current source. Voltage sources, ideally, a voltage source produces Vs volts, produces volts, 10 volts, 20 volts, etc. Vs volts, regardless of the current absorbed or produced by the connected device. But the current source, ideally a current source produces IS amps, 1 amps to 10 amps, IS amps, regardless of the current in the connected device. In a particular circuit, in a particular case, there can be active elements that absorb power. For example, a battery being charged. Passive elements are the elements that can't generate energy, such as resistors, that we denoted as R. Resistors dissipate energy. heat energy, capacitors, and inductors. The unit of resistors, how we measure the resistors in ohms, and this is the symbol of ohms. Ohm, 1 ohm, 2 ohm, 3 ohms. This is the symbol of the resistor, resistance of a wire. R is equal to rho multiplied by L over A. What's rho? Rho is the resistivity in ohms. L is the length in meters. And A is the cross-section area in m squared. Conductance, G of a pure wire. This is the inverse of the resistance, 1 over R. We measure it in mho. As you see, mho is the reverse words, the reverse letters of ohm. The symbol is the same, you just need to flip it vertically, to flip this symbol of the resistance in this way, vertically. This is mho. Another way to measure the conductance is Siemens. We measure it in Siemens, S, capital S. We have also two types of sources, dependent and independent sources. The independent explained in the previous slide, like this one, this one. What are dependent sources? Dependent sources of voltage or current sources, we denote it like this. What does independent source mean? See, I1 2 times I1. This is I1. So this source is dependent. Why? Because it depends on another current, I1. You see, if you find I1 or if you know I1, you can find this source. So it's related to this current. The same thing with this dependent voltage source, because it depends on V2. This is V2. If this voltage changes, this dependent voltage source will change. Resistors in series. If we connect two resistors in this way, by connecting them in one terminal only, the other terminals will be connected to the circuit. So in series, it means they are connected in one side only. Both of them are connecting in one terminal. This is the terminal of R1 and this is the first terminal of R2. The other terminals of each of them will be connected to the circuit. This is the way how we connect resistors in series. This is the current. If these resistors are connected to electrical circuit, and the current will pass through them in this way. The current in resistors in series will be the same. So the current here is the same after passing through R1 and is the same through IR2 and still the same through after passing through R2. We can find the total resistors in series. We call it equivalent resistor. How we do that? Simply you just add up the values of the resistors. R1 plus R2 is the equivalent resistor. The equivalent symbol, you can draw it as one resistor and write here R equivalent or the value, the total value that you found here. Here another example about resistors in series. 4 resistors in series, the equivalent resistor is the summation of the four resistors, R1 plus R2 plus R3 plus R4. And again, you can draw them using one resistor only and write the total value that you found here, the equivalent resistor. Ohm's law. This is the most important and the basic law that we use in electrical circuits. I is equal to voltage over R over resistance. For example, if we have this circuit, this is the active source. This is a plus and this is minus. These are the two terminals, A at the negative terminal, B at the positive terminal. If you are not given the direction of the current, you can draw it yourself, starting from the positive terminal of the active source, the voltage active source in this direction, and you continue in drawing this current that flows through this circuit. As you see, continues here, passes through R1, leaves positive here, as we explained in the first slide, and negative here. So this is the voltage over R1, continues, passes through R2, leaving positive at this point and negative at this point, continues in flowing through the circuit, passes through R3 before it passes through RT. This is high potential, passes through it, and here is the negative potential. And here we have V3, V2 here over the voltage of R2, V3 the voltage over R3. Continues in flowing to complete the circle here, and this is the complete circle of this circuit. Starts from here and enters again to this terminal, the negative terminal of the active voltage source. These resistors, as you see, R1, R2, R3, they are connected each other. R1 is connected with R2 by one terminal. This is the terminal, the second terminal of R1. This is the first terminal of R1 connected to the voltage source, but this terminal is connected to the first terminal of R2. So they are connected in series because one terminal only is connected from each of these resistors, R1 and R2. The same thing for this R2. This terminal is connected to this R3. So these three resistors are connected in series. Now we can sum up the values of these in series resistors to get the equivalent resistor, as we learned from this explanation that we can draw it as one resistor, only the equivalent resistor. And this is the way how you connect the equivalent resistor to the main source or the voltage source. This is the equivalent circuit, the equivalent resistor, and the equivalent circuit with it, inside it. And this is still the same current because they are connected in series. The current is the same, and the current is the same here as well. This is another example. Here we have 5 resistors connected in series, and as you see, this is the main current, the total current. But because the resistors are connected in series, so the current is the same. The main current, the total current, is the same as the current that passes through each of these resistors. It's the same. You see, it's the same, and again it flows and go back to the main or to the active voltage source. Now we want to use the Ohm's law to find this current. The voltage is 9 volt of the circuit connected between this terminal and this terminal. As we learned, we can find the equivalent circuit. So the equivalent circuit is 90 ohm. And this is the schematic of the equivalent schematic of this circuit. See, this is the equivalent resistor. 20 plus 20, 40, 60, 80, 90 ohm. This is the equivalent circuit. And these are the points that we mentioned here. You see, this point is this point. This point is this point. And these are the resistors. Now, the equivalent resistor is this one. So now we have a simple circuit. We can find the current. We have the voltage here, according to Ohm's law. We have a resistor here, one resistor, one equivalent resistor, 90 ohm. We write the Ohm's law 9 over 90, 9 volt over 90 ohm. The result is 0.1 amps. Or we can write it in milliampere, 100 milliampere. Simply you multiply this number by 1000, you will get the result in milliampere. We can write the Ohm's law in this way. You simply just swap this with this. R, take R here, and I put it in the denominator. You will get this. So R is equal to voltage over current. Or you can write it also here. Now R over 1, you can multiply R by I. So you will have R times I, and V multiply V by 1, you will get V here. To find the current in this direction, you know we solved such example in the previous slide. I is equal to voltage over the equivalent resistor. This is the equivalent resistor. Here we wrote it as R1 plus R2. This is the equivalent resistor. Fine. Now, see, here is, we will write here V1 to denote the voltage across R1. And the voltage is, V1 is equal to I, the current, which is the same, the total current is the same as the current that passes through R1. The current multiplied by the resistor R1. I is equal to this formula. So we took this formula and wrote it here. So the voltage now, voltage across this resistor that is connected in series with another resistor, only two resistors we have here, is equal to the total voltage here multiplied by the resistor R1 that we take the voltage across it over the equivalent resistor. What is the benefit of this formula? You see here, we can find the voltage of one of the resistors that are connected in series. If we have two resistors only in series, we can find the voltage of one of them without the need of the current. You see, here we have only resistors and the voltage. Voltage, the main voltage, the total voltage, multiplied by the resistor that we want to find the voltage across it over the equivalent resistor. The same thing you see, and we can rearrange this formula and write here the total voltage R1 over the equivalent resistor. The same thing we can do for the second resistor in the same way. See, I, because I is the same, because they are connected in series, I multiplied by the resistor R2. We use this equation, this formula, write it here, multiplied by R2 here, and again we rearrange this formula to get this one. You see, you can see now V2 is equal to the total voltage here, you see, multiplied by the resistor that we want to find the voltage across it over the equivalent circuit. We call this voltage division. This, as I said, this helps us to find the voltage across only two resistors in series. For more resistors connected in series, you have to find it using the regular formulas. You cannot use this for more than two resistors in series. Voltage division only for two resistors in series. Resistors in parallel. What if we have two resistors in parallel? What does in parallel mean? It means to connect two resistors. Both terminals of two resistors are connected together. You see, this resistor R1 is connected, this wire, you see this wire is connected with the other terminal of R2. The second terminal of R1 is connected with the other terminal of R2. So both terminals are connected with each other. This is in red, you see, R1 with R2. R1, the other terminal, R1, R2. So both terminals are connected together. But in series, you see only one terminal of each of them is connected together. The other terminals, the other sides of each of them are connected to the rest of the circuit. The current flows in this direction. It goes to this direction and this direction. So it will be distributed into two directions. Why? Because we have this branch and this branch. So we have here I current for R1, and here we have the current that flows through R2. This architecture is the same as this one. The currents will be distributed into two branches. Each branch in this circuit has one resistor. This is I1 and this is I2. So it's not the same case as the resistors in series. The resistor in series, the current is the same. But here, I1 is different from I2 is different from I. So we have here different principle for resistors in parallel. I1 here passes through R1 and continues here flowing through R1 until it reaches this point. I1, the same as the current passes through R1, the same current I1 continues because the same way, the same direction. So I1 is the same through this branch. I1 it means the same value until it reaches this point, this node. The same thing for I2. I2 is the same. The same I2 that passes through R2 is the same as this one. I2 is the same as this one and this one. Continues in this direction, the same I2 until I2 reaches this node. At this node, I1 will be added to I2, and both of them will go into this direction. This is I. It is the same value of this current. So this current distributed into two branches, and they are added together at this node, and again we have the same value, the same current I. The same current continues flowing through the circuit until it reaches or enters the battery from the negative terminal. The equivalent resistor for resistors in parallel, for equivalent circuit in parallel, is as follows. The formula, the main formula, the standard formula of resistors in parallel is 1 over R equivalent equal 1 over R1 plus 1 over R2. And the result is as follows. R equivalent is the multiplication of the two resistors over the summation of the two resistors. This equation is valid only for two resistors. So you can memorize this for only two resistors in parallel. For more than two resistors, this is the equivalent resistor, R equivalent. This value is obtained from this formula. And this is our very simple circuit. We have here voltage, we have current, and resistor. Here is a circuit that contains more than one resistor, R1, R2, etc. to Rn. And this is the equivalent resistor. How you find this equivalent? Using this formula. Or this is in general. This is the formula for any resistors connected in parallel. 1 over R1 plus 1 over R2 plus up to 1 over Rn. Rn you have 4, 5, for example, resistors, R5, for example. We will work on this circuit that has only two resistors connected in parallel. The total voltage here is equal to the total current multiplied by the equivalent circuit, the equivalent resistor. This is the equivalent resistor. You have to find the equivalent resistor. After getting the equivalent resistor, you will have this terminal, this point, and this point, and you will draw only one resistor. I is equivalent to R equivalent. R equivalent for these two resistors in parallel, as we explained in the previous slide, is equal to the multiplication of both resistors over the summation of both resistors. This is R equivalent. Fine. Now, the current of I1, remember, the current here is different from the total current. Okay, because this current I1 and I2, the summation of both currents are equal to the total current. So I1 is different from I2 is different from I. So we need to find I1. How to find I1? I1 is equal to voltage over R1. Which voltage is this one? Why? Because we need the voltage across R1. We need to find I1, so we need to find the voltage V1 across R1. But R1, this voltage source is connected between this point and this point. So the voltage V1 is the same, similar to the total voltage, to the voltage source. So V1 is equal to V. The current is equal to V over R1. V is equal to this formula. We wrote this formula as is here in the denominator over R1. We will rearrange this formula. You see, at the end, to find I1, the current across this resistor in this branch, we do not need the voltage here, any voltage. It's enough to have I and the values of the two resistors connected in parallel. The same thing we will do to find I2 across R2 in this branch. Be careful when you want to memorize these four equations. In series, the total voltage multiplied by the resistor that you want to find the voltage across it. See the current in parallel, the current that you want to find, the current across the resistor. Here, the resistor is the other resistor, not the same resistor. This is the difference when you want to memorize. Be careful about this difference, okay? So we call this current division. We will solve this example using our information that we obtained in the previous slides. We have this electric circuits with a voltage source, 24 volt, with four resistors. In this example, we want to find the current, the total current in the circuit. The total. You have to understand how this current flows. This is the total current that flows from this voltage source. You see, from positive terminal across R1. So R1 is connected in series. We can say in series, not only for resistors or only for in parallel for only resistors, because this is a principle of connection. R1 and this voltage source are connected, each of them in their own one terminal. You see, this is terminal of the first terminal of R1, and this is the first terminal of the voltage source. The other terminals are connected to another nodes or another elements of the circuit. So because they are connected in one terminal, they share one terminal of each of them. This is why we can say that this voltage cell is connected to this resistor R1 resistor in series. Why we need to understand this principle in general? Because by knowing that this voltage source is connected in series with R1, this allows us to understand that this current, the total current, is the same as the current flows through R1. So if we write the current here as I R1, that means the current that flows through R1 is the same as this total current. Then this current will continue. So there is no need to write IR1 here. We can write I because it's the same current as we explained until it reaches this node. After reaching this node, this current will be distributed into the two directions, this direction and this direction. So the current here is no more the same as this current, the total one. and this current that flows through this branch is not the same as this one. Okay. Now we have two branches that this total current flows now. Two branches. This branch has only one resistor, 10 ohm R2, 10 ohm resistor. It continues the same current through this resistor, the same current, until it reaches this node, and we stop at this node. Okay, the same just in this branch. What about the other branch? The other branch, we have two resistors, R3 and R4. See how they are connected. Because they are connected in only one terminal, they share one terminal with each other. So they are connected in series. We have one branch and one current that flows that is the same in two branches, in two resistors. R2 and R4 has the same current. The same current flows this branch. Is the same. The current that starts after entering this branch is the same current that flows all the way through this branch until it reaches this point, this node. Then both currents will be added again together. The value of the result of these two currents is the same as this one before entering this node. So how we solve after understanding the philosophy of connection of resistors and flowing of the currents through branches, how we start? First of all, we will start by adding the two resistors R2 and R3 and R4 in series. We will sum up their values together, R3 plus R4. So 6, the value of R3, plus 4, the value of R4, equals 10 ohms. The equivalent circuit so far is, as you see in this architecture, in this schematic. We have R equivalent here, 10 ohm, that corresponds to these two values, these two resistors R3 and R4. Because they are both connected to this point and this point or this point, so this point corresponds to this point. This point corresponds to this point. So they were connected to both points here and here. The equivalent will be connected to the same points, this one and this one. This is our equivalent of R3 and R4. This will simplify viewing the new architecture of the new circuit. We can see R2 and R5. The equivalent of the two resistors connected in parallel is multiplication of both resistors over the summation of both of them. The result in value is 5 ohm. If you have two resistors in parallel and both of them have the same value, see the value here is 10. The result should be half of this value. See, we have 10, 10. You have to predict that the result should be 5. See now, these two resistors connected in parallel, R2 and R5, are connected to the original circuit in this point and this point. So this is the point that were connected, and this one. Here where we will connect the equivalent circuit, the 5 ohm. And see, now we have very simple circuit. And you know now we have two resistors connected in series. One current passes or flows through both of them. Very simple. Two resistors in series, we sum up their values. As you see, we will call it R7. The equivalent circuit equals R1. This is R1 7 ohm plus R6. This is R6. Its value is 5 ohm. The total is 12 ohms. The final equivalent circuit is this. 12 ohms is the equivalent circuit. Both of the previous architecture or previous view of the circuit, two in series resistors R1 and R6, their terminals were this point and this point. They are connected in series, and this is the first point of the two resistors, and this is the second point. So we found the equivalent value. We connect the equivalent to the same point, this point and this point. Now it's very simple to find the current that's required in our example. We have, according to the Ohm's law, the current is equal to the voltage over resistor. The current is this one that's required from us. The voltage is already given, 24 volt, and the resistor is the final equivalent resistor, which is 12 ohm. The result is 2 amps.